Okay, I know. If I still don't tell you the reason why they are of different color at different temperature, you're gonna punch me in the face. So far we have talked about two equations in total. The first one is called the Stefan-Boltzmann equation, which tells you the relationship between temperature, surface area, emissivity to the radiation powered. So the second equation that we have is the Wings Displacement Law. Sorry, I didn't describe or define it very well in the last video. So what it actually tells you is for whatever object actually, as long as you have temperature, then you would emit electromagnetic waves actually. The electromagnetic waves that you emit is not a single wavelength, okay, or a single frequency. You are actually emitting a spectrum of wavelength. And so that's why this is an observation that made by obviously a scientist called Wing, that the relationship between the maximum intensity wavelength, so again, maximum here is not referring to the wavelength that is maximum, it's referring to the intensity, which is the maximum amongst all, and that obviously is referring to the one that is showing to you, obviously. And so this is the equation that governs the relationship of what color or what is the EM wave that you can detect the most. Let's check the Wing's law by applying it to Bunsen burner first. So as we said, the blue flame will have a greater temperature while the yellowish flame will have a lower temperature. Again, this is done by measurement. So it's nothing to do by saying or prediction from Wing's law. No, that's not the case. We simply use a tool. So it could be thermocouple to measure its temperature, and we find out blue is really higher simply. And then the next thing is to think about the wavelength of these two colors, because again, the reason why you see it as blue or see it as orange or yellowish is because that particular color has the greatest intensity that's emitting to your eye simply. So you actually are required to remember the wavelength of different color in IB physics, and it should be around 300 nanometer or 400 nanometer to 700 nanometer. Okay, and so in case you don't remember, let me show you a diagram. So you can see the red one is roughly about 700, and then the violet one is about 3 to 400 nanometer. So that is to say, the blue light will have a lower wavelength, and the orange or yellowish light will have a greater wavelength. So if you fit that back to the equation, it will make sense, because when one decrease, one would increase on the left hand side of our equation, because the whole thing should be a constant. So we are very happy that the Wings displacement law align with our observation. And let's think about the case when we are talking about the sun now. Okay, so the question is, how come the sun is white in color? Because from our observation, again in Bunsen burner, we see that when things get hotter, it should get to blue, or maybe, by induction, then maybe the sun can be a violet color. So why would it be white, which is a mixture of all the color? Let's try to apply Wings displacement law and see what happened. So right now we know somehow is temperature, and let's see what we will get when we substitute it in. Remember to use the Kelvin scale. Alright, so if you try to use your calculator, you should be able to find a number that is 5.02, right, 365 times 10 to the power of negative 7, and that should be in meter. So do you know what kind of wave is it? And you should be able to get the answer of maximum intensity of wavelength to be about 5 times 10 to the power of negative 7 meter, which means 500 nanometer. So if you check out the visible light spectrum here, you can see that 500 nanometer is about the color of blue to green. Oh my god, that means we have been learning the color of sun wrong. It should actually be blue and green for the sun.
NANI?
First of all, the reason why the sun appears to be white is because the color of different visible light are just so strong that when it comes to our eye, we just perceive it as a mixture of all colors. So that's why it is white. The other reason why sometimes the sun appears to be more like yellowish or reddish, especially when it sunsets, is because of the atmosphere will scatter most of the blue light. And so that's why the blue light is kind of taken away, leaving you with the yellow and red color. So that's why the sunsets are always red or orange in color. And here is another picture showing you that from the space without the atmosphere, you can then see the sun in white color as well. By the way, since we have mentioned that green or blue light should be of the greatest intensity from the sun, then if you try to shift the wavelength further, then you go to violet and also the ultraviolet. So that's why sun would provide you great deal amounts of UV light, right, which may potentially be dangerous for your skin and body. Lastly, back to human. So why do we emit infrared then? The answer is simple. What you have to do is simply try to apply the Wings Displacement Law on a human body temperature, that is 37 degrees Celsius. So let me show you how to do it. Okay, so the equation once again, let me write down. Lambda max T equals to 2.90 times 10 to the power of negative 3. And so the wavelength is what we want to find. And for the T, remember, it's in Kelvin scale. So 37 plus 273 equals to 2.90 times 10 to the power of negative 3. And you can find the answer as something like 9.35 times 10 to the power of negative 6 meter. So if you try to check this in the spectrum, you can then find this should be around here, which is the infrared. So that's why, because of our body temperature is roughly, well, constantly 37 degrees Celsius, or even if you have fever, it's just maybe 1 degree higher. So it's still infrared only. So that's why our body mainly is emitting the infrared. Back to this example, if you try to calculate the Earth surface temperature as well, you should also find infrared. So that's why when we talk about later on about greenhouse gases, infrared is one of the issue because Earth itself is emitting infrared, and those greenhouse gases which can trap infrared will be potentially a problem if we get too much of greenhouse gases. Here is a very interesting question. Can you think of one application that you can use by Wings Displacement Law? So of course we are not talking about just now when we try to find out what is being emitted by the human body or Earth or Sun. So are there any other applications that you can use in general for Wings Displacement Law? My answer is actually for astronomy, and that is by observing what kind of wavelength you can receive from a certain planet, then you can guess its temperature. So this is a great tool when you try to observe and do measurement, because there's no way you go to that particular planet which is really far away and you use a thermometer to measure it. So this is one very good way we can rely on and measure the temperature of a planet. If you have other suggestions, please tell me in the comment section below. That's all for this video. So next time you can tell your friends who doesn't study physics that the sun is actually green or blue in color.